Equilibrium, as I said, is a condition in which everything in the every part of a substance in a system reaches the or yeah every part of a substance in a system reaches the same temperature. So we saw an example in which we put a hot piece of metal, or a blacksmith put a hot piece of metal in water, and the metal and the water both reach the same temperature. Well, what happens if you take two volumes of water and combine them with each other? Here we see an 80-degree glass of water being poured into a 10-degree bowl of water, and they only reach an equilibrium temperature of 15 degrees Celsius. A glass of hot water poured into a bowl of cool water. The average temperature is reached when the water achieves a state of thermal equilibrium. It's all water, water added to water. Why is it 15 degrees Celsius? Why isn't it 45 degrees Celsius, which would be halfway in between? Just because they reach thermal equilibrium doesn't mean that the temperature is exactly in the middle of the initial temperatures of the two objects. In this image, why does the temperature end up at 15 degrees Celsius? Why do you think the equilibrium temperature is much closer to the initial temperature of the bowl than that of the glass? Well, the bowl has a significantly larger amount of water in it than the glass does. So a small amount of 80-degree water isn't going to raise the temperature of a huge bowl of 10-degree water by half, by the midpoint between them. Okay, so if you add a small amount of hot water to a large amount of cool water, it's going to have a smaller effect on it than finding the middle temperature. So the equilibrium temperature is going to have something to do with the volume, as well, or more precisely, with the mass of the substances and the starting temperatures. If you were to pour a bowl of boiling water in the ocean, it would have almost no effect, right? On the ocean, the boiling water would get up to ocean temperature almost, or get down to ocean temperature almost. Mass is one consideration that you have to keep in mind when thinking about thermal equilibrium between two objects. If we have a kilogram of lead and a kilogram of silver, and 20 degrees, the lead is 20 degrees, the silver is 30 degrees, you put them together, then we might expect the temperature to end up being halfway in between. But then we have one more property that we need to consider, which is specific heat capacity. Specific heat capacity is the quantity of heat required to raise a unit mass of homogeneous material. In other words, just a very consistent amount of material. 1 Kelvin, or 1 degree Celsius, in a specific way, given constant pressure and volume. Or more simply put, it's the amount of heat it requires to raise the temperature of an object by 1 degree Celsius, or raise the temperature of a kilogram of an object by 1 degree Celsius. If we look at these images, why is it that we end up with the kilogram of lead heating up more than the kilogram of silver cools down? Why is the temperature of the thermal equilibrium closer to the block of silver than to the block of lead? Well, they're the same mass, so it must have to do with this property, specific heat capacity. It takes more energy to change the temperature of a kilogram of silver than it does a kilogram of lead. Lead heats up and cools down more easily than silver does. So lead has a lower specific heat capacity than silver.